Hey everyone, this is meteorologist Ben Price at the National Weather Service in Springfield, and welcome back to another Weather Unlocked session. This is video 35, and we are going to be talking about instability. This is a weather term that you may hear be used quite frequently when it comes to thunderstorms and severe weather in the forecast. But what exactly do meteorologists mean when they mention instability, and how does it exactly produce thunderstorms and severe weather? You'll learn the answers to those questions in this video. So without further ado, let's jump into it. So first up, what exactly is instability? Well, it actually means different things depending on which line of scientific work you are in. In physics, it simply generally means that an object or system can have some sort of output or internal state that increases with time. For example, this ball resting on top of a bowl has instability. At the moment, it is at rest, but if you were to nudge it, it would fall and accelerate downward all on its own, thanks to gravity. In meteorology specifically, instability is the ability for a parcel, or in other words, a bubble, of air to rise freely without any outside force to keep it going, thanks to buoyancy. So in our case, if the air is warmer and less dense than the air around it, it will rise freely because it is more buoyant. You can relate that to something floating up to the surface in a body of water because it is less dense and more buoyant. And in terms of this cumulonimbus cloud here, it is growing because of instability. Warm air from the surface is rising and is able to rise freely as it's less dense and warmer than the environmental air surrounding it. So let's dial it back a bit and explain instability a little bit better with a simple analogy, a hot air balloon. So before anything begins, the balloon is sitting at the ground because the air inside it is the same temperature as the surrounding air. Once the operator starts up the fire beneath the balloon, the air inside the balloon begins to warm up. The warm air inside becomes less dense than the surrounding air. In a nutshell, this is because the air molecules inside are getting energized by the heat and moving around faster than the cooler, slower air molecules outside the balloon. Since the air inside the balloon is warmer and less dense than its surrounding air, it is now considered unstable and will rise. It will keep rising as long as the air inside is warmer than the air outside. To come back down, the fire basically needs to go out so the air can cool to the surrounding air temperature and then start to sink. Now let's bring that previous example to the atmosphere. First, the sun heats up the ground, which warms the air just above it. And as with the hot air balloon, the warmed air becomes less dense than the surrounding air. From this, an air parcel, or bubble, begins to rise. And as long as this parcel is warmer than the air around it, it will continue to rise freely because it is less dense and therefore more buoyant. In other words, it floats up. If this air also holds a good deal of moisture, the rising and cooling will condense the moisture into clouds. And if the air parcel is much warmer than the surrounding air, it will rise rapidly and form thunderstorms. Now, if you've been paying attention in our Weather Unlocked series, or know a thing or two about the atmosphere yourself, you may be asking, doesn't the temperature decrease as you go up in the atmosphere, like always? So shouldn't the warmer air near the surface always just rise? And that's a valid question, but that's where things get a bit tricky. Because that warm air that starts rising also cools as it rises. This is why clouds are able to form in the first place, because the air cools and condenses any moisture out into clouds while it rises. So that means that the rising and cooling air must still always be warmer than the air around it in order to continue to rise. In other words, the rising air needs to cool at a slower rate than the rate at which the surrounding air temperature decreases with height. Now that may sound a bit confusing, but we'll try to explain it a little bit better here for you. And you also may be wondering, so if air is cooling as it rises, how are we exactly able to determine if there is instability in the atmosphere? And how are we able to measure the magnitude of that instability? Well, buckle up, folks. This is where it gets a bit more fun, but also a bit more complicated. So in order to determine instability, we need to see what the temperature and moisture profile looks like through the atmosphere. We do that by plotting our weather balloon data on what's called a Skew-T diagram. I'm going to explain these rather quickly, but we have a much more in-depth video on this way back to our third Weather Unlocked video, so please refer to that video if you'd like even more information. Anyways, the Skew-T chart has temperature lines, pressure lines, which basically act as height on the y-axis, so decreasing pressure is increasing height. Mixing ratio lines, which basically denotes the level of moisture in an air parcel. Dry adiabat lines, which kind of sounds confusing and fancy, but it's basically just showing the rate that dry or unsaturated air cools when rising. And then we have moist adiabats, which is kind of the same thing, but it's the rate at which moist or saturated air cools while rising. The rates are different for saturated versus unsaturated air because when air is saturated, it condenses into clouds, which releases more heat. That means that it's going to slow down the cooling process of that air that's rising. So basically, saturated air cools at a slower rate than dry air. It stays warmer longer. Now this graph is called a Skew-T because the temperature lines on the x-axis are skewed, from left to right, for easier interpretation of the vertical profile of the atmosphere. So now that we've got that out of the way, let's go through an example of how we determine instability. Here's a Skew-T with temperature and moisture plotted from a weather balloon launch. The red line is temperature and the green line is moisture, or dew point. So first, we take the temperature and moisture at the surface. This is usually the warmest point of the atmosphere and therefore the greatest potential to rise. This parcel of air is warmer than the surrounding air, so it rises. But remember, it cools as it rises at the rate of the dry adiabat, which is this line shown here. So if we match that line up with the temperature point, we can see that the path that it takes while rising. So we can see it's generally the same temperature as the environment. Next, we have to take into account how much moisture we have as we rise. This will stay at a constant ratio, so it will follow this purple line, or the mixing ratio line. Where the red and purple lines intersect is where the parcel becomes saturated and starts producing clouds. So now, our parcel is where this blue dot is. Now that it's saturated, our parcel cools at a different rate because it is condensing out the moisture. Now it cools at the moist adiabat line. If we match that up with our parcel position, we now get the next path the parcel follows. We can see that this line to the right of the is to the right of the environmental temperature. So here's our environmental temperature, the red line, and the green line is our parcel path. So it will rise freely. Well, this line is to the right, which means that it is warmer than the environment. If it's to the right, it's warmer than the environment. So that means that it will rise freely until it intersects the environmental temperature line again, which is all the way at the top here. Now where that blue dot is. So now that we've traced the path our parcel takes while rising, we can determine the amount of instability. Simply put, it is the area between the parcel path line, that green line, and the environmental temperature line. This yellow shaded area is our amount of instability. The larger the area that it is, the greater the instability. Now, let's dig a bit deeper. Now that you know how to determine the amount of instability, what actually creates it? Instability can be increased through three main ways: increasing the surface temperature, increasing the moisture at the surface, and or decreasing the environmental temperature above the surface. The opposite of those will decrease instability. So for example, what if our surface temperature in this profile was warmer? So we move our surface temperature dot to the right, and we can draw our new dry adiabat line for it to follow, and find the new saturation point, which again is where the purple and the red line intersect. Now you can see that the new path it follows creates a larger area between the parcel path and the environmental temperature line. See now that our green line has moved to the right. This means that the instability has increased. So increasing surface temperature increases instability. Let's reset and now ask what would happen if we decrease the moisture at the surface. So let's get rid of our moisture profile there and move it to the left a little bit. We've decreased our moisture. From our new moisture point, we can draw the new mixing ratio line and find where it intersects the dry adiabat line, which is the dark red line, for our new saturation point, the blue dot. Once again, we draw the new parcel path, and as you can see, the whole path is to the left of the environmental line. So this dark green line here is to the left of our red temperature line. This means that the parcel path is cooler than the environmental temperature anywhere in the atmosphere. That basically means that the parcel cannot rise and there is no instability whatsoever. No parcel would be able to rise here when there is decreased moisture. So in this case, there's no instability because there is less moisture. Lastly, what happens if we decrease the environmental temperature above the surface? Let's say our new environmental temperature line is this new red line here. The parcel path stays the same. So that means our instability area is bigger, and therefore we have more instability. The new shaded area is our new instability. measurement, and it's larger than the one from before. So that's all the ways that you can increase and decrease instability and how we find that measure of instability. Now here's a quick note. All throughout the video we've been talking about surface-based instability, meaning that the rising air originates at the surface. There are different types of instability that we won't go into here, but basically air can begin rising anywhere in the atmosphere, not just the surface. If a rising parcel originates above the surface, any instability resulting from that is called elevated instability. And mixed layer instability is basically a parcel consisting of the average near surface temperatures rather than the temperature right at the surface. Alright, we're almost finished. So how does this all relate to severe weather? Well, we kind of answered that along the way. The presence of instability means warmer, less dense air is able to freely rise throughout the atmosphere. The greater the instability, the more potential energy there is for air to rise rapidly and create storms, especially when there is increased moisture. In the next Weather Unlocked video, we will discuss why even with a ton of instability, storms may not even form at all. So stay tuned for that. Well, thanks for listening to this session of Weather Unlocked. I hope you were able to learn something today about instability. Make sure to follow us on all the socials for any weather information, and stay tuned for the next session, which will be on a capping inversion. Bye now.